Hi, I'm Jeff Groh, and this is Calculus 2. Today, we're going to talk about power series, as with most new topics, we begin by defining our terms. A power series is a series of the form the sum as k goes from 0 to infinity a sub k x minus x naught to the power k. There are some things that we should note before moving on. First, the power series has a variable x. That means you end up with a function, something that will depend upon the value of x that you choose. These are centered at x naught. And from the outset, you're not guaranteed that this will converge as a series at any point except x naught. It will always converge at x naught, because when x is equal to x naught, you get a bunch of zeros. The only potential term that might survive and not be zero is the k equals 0 term, because a naught will be that first term. What is more, a power function is a function of the form a constant times a power of x. As you can see, power functions are being summed here. If you FOIL this out and combine like terms, you'll get a sum, an infinite series of power functions, and that is why these are called power series. Let's give some examples. Sum as k goes from 0 to infinity of x to the power k. That's about as simple a power series as you can get. All of the coefficients are 1, and the center is 0. It is natural to ask, for what values of x does this series converge? But we can also answer another question on this very simple series. To what value does the series converge? In this case, what we have here is a geometric series. With the common ratio equal to x. That means that if the series does converge someplace, being an infinite series beginning at 1, that means the sum is 1 over 1 minus x. That's using that form for the sum of an infinite geometric series being the first term divided by 1 minus the common ratio. A geometric series of the form the sum as k goes from 0 to infinity of a r to the k. Sure, it adds up to a over 1 minus r, but it requires that the common ratio have a magnitude less than 1, and it diverges for other common ratios. In this case, we're dealing with the sum as k goes from 0 to infinity of x to the k. The common ratio is x, so we only get convergence provided the absolute value of x is less than 1. Notice that the set of x values on which the power series converges is an interval from -1 to 1. We have what is called an interval of convergence. For some power series, there's a special formula for the radius of convergence and interval of convergence. Let's suppose we start with the sum as k goes from 0 to infinity, a sub k, x minus x naught to the power k. We can use the ratio test to determine the x values for which this series converges. And here's how we'll do it. We'll take the limit as k goes to infinity of the absolute value of a k plus 1 times x minus x naught to the power k plus 1 all over a sub k x minus x naught to the power k. To get convergence, we require that that limit, if it exists, must be less than 1. As you can see, we do get a lot of cancellation here. This x minus x naught to the power 1 inside of the absolute values does no longer depend upon k. We can bring this out of the limit in absolute values to this location here, since it no longer depends upon k. We'll just have the limit as k goes to infinity of the absolute value of these coefficients a k plus 1 over a k. If that limit exists, we can divide it off of the inequality. We'll have the following. When you divide by a fraction, you may invert that. You invert and multiply. We end up with what looks like an upside down ratio test. We'll call the value on the right-hand side r for radius of convergence. As you can see, we only get convergence when the absolute value of x minus x naught is less than r. This is a formula, by the way, you need to remember. This absolute value inequality can be solved adding x naught to all three parts. We only get convergence for x values between x naught minus r and x naught plus r. This won't be necessarily the interval of convergence. However, it certainly will contain the interval of convergence. Why won't it be exactly the interval of convergence? Because the ratio test fails when you get equality with 1. So when we have equality up here or equality down here, the ratio test fails under those conditions and tells us precisely nothing about convergence or divergence. If the inequality is the other way, we get divergence according to the ratio test. So points less than x naught minus r and points x bigger than x naught plus r will be points where the power series diverges. The only question mark is, what about the endpoints? Those must be tested separately. If I is the interval of convergence, then I will contain the interval x naught minus r to x naught plus r. For example, suppose I have the sum as k goes from 1 to infinity of x to the k divided by k. I'm starting at 1 here to avoid division by 0. In this case, the center is 0. You have nothing subtracted from x. and so nothing is where the center is. The radius of convergence is the limit as k goes to infinity. Do you remember the formula? ak divided by ak plus 1. In this case, a sub k is 1 over k. You take only the coefficients of the powers of x for the coefficients a sub k. Very important that you remember that part. This will be the limit as k goes to infinity of 1 over k divided by 1 over k plus 1, and that's 1. This means that the interval of convergence contains everything from 0 minus 1 to 0 plus 1. We get convergence. In fact, at each point in this interval, the original series will converge absolutely. When you get when x values are strictly bigger than 1 or strictly less than -1, this series will diverge. The only open question is, what happens at the endpoints, at -1 and at 1? That must be checked separately. At x equals 1, we have the sum, as k goes from 1 to infinity, of 1 over k. That's the famous harmonic series. And the harmonic series famously diverges. At x equals -1, we get the alternating harmonic series. And the alternating harmonic series famously converges, conditionally, but it converges. We deduce then that the interval of convergence is equal to the interval including -1, but not including 1. As another example, suppose I have the sum, as k goes from 0 to infinity, of x to the k divided by k factorial. In this case, the center is 0, and a sub k is 1 over k factorial. The radius of convergence will be the limit, as k goes to infinity, of 1 over k factorial divided by 1 over k plus 1 factorial. As you can see, this fraction will invert and multiply, giving you a k plus 1 factorial here. Factorials cancel in this way. In the limit as k goes to infinity, the radius of convergence is positive infinity. It follows immediately that the interval of convergence is the entire real line. If the series is the sum, as k goes from 0 to infinity, of k factorial x to the k, again, the center is 0. The coefficients in this case are k factorial. The radius of convergence is the limit, as k goes to infinity, of k factorial divided by k plus 1 factorial. We end up taking the limit of 1 over k plus 1 as k goes to infinity. We obtain 0. That means the interval of convergence is really just a set that contains only the center, 0. I think you can see that for a power series to converge, the coefficients have to go to zero fast enough. In this case, the coefficients don't go to zero, they blow up to infinity. So you only get convergence at the center for this particular series. If we have the sum as, let's say, k goes from 0 to infinity of 3 times x minus 1 to the power of k, for what values of x does this series converge? The center this time is 1, and the coefficients are all 3. So the radius of convergence will be the limit as k goes to infinity of 3 divided by 3, which is 1. Since the center is 1, the interval of convergence will contain everything from 0 to 2. What happens at 0? We have the sum as k goes from 0 to infinity of 3 times negative 1 to the k. While this is an alternating series, the terms don't go to 0, which means that this diverges by the divergence test. The same is going to be true at x equals 2. Because when x is 2, 2 minus 1 is 1. 1 to the power k is 1. So this also diverges by the divergence test. The terms simply don't go to 0. We deduce then that the interval of convergence is everything from 0 to 2, not including either of the endpoints. Power series will converge everywhere on the interval of convergence, but that interval may or may not include one or more of the endpoints. It could include both. As an example, consider the sum as k goes from 1 to infinity of x to the k divided by k squared. Here, the center is 0. The radius of convergence will be the limit as k goes to infinity, absolute value, 1 over k squared times k plus 1 squared over 1. I'm inverting and multiplying. Since we get a quadratic over a quadratic, both with leading coefficients of 1, the radius of convergence is 1. That means the interval of convergence will contain everything from negative 1 to 1. The only question is, what about the endpoints? If we try negative 1, we get the sum as k goes from 1 to infinity of negative 1 to the k over k squared. This, as an alternating series, converges by the alternating series test. It's pretty easy to implement the alternating series test to prove this. At x equals 1, we have a p-series, p equals 2, which is greater than 1, and therefore it converges. We see then that the interval of convergence is equal to everything from negative 1 to 1, inclusive of the endpoints. Suppose we have the sum as k goes from 0 to infinity of negative 1 to the k, x plus 1 to the k, divided by 2 to the k. The center in this case is negative 1, and the coefficients are negative 1 to the k over 2 to the power k. The radius of convergence is the limit as k goes to infinity, absolute value Since we're doing this in absolute value, these powers on -1 won't matter. Inverting and multiplying by what we get when we use k plus 1 instead, k factors of 2 will cancel, leaving a radius of convergence of 2. The center is -1, so the interval of convergence will contain everything from -3 to 1. You go -1 minus 2 and -1 plus 2. We have yet to test the endpoints. At x equals 1, we have the sum. As k goes from 0 to infinity, -1 to the k, 1 plus 1 is 2 to the power of k over 2 to the power of k. While we do end up with an alternating series, the terms don't go to 0. So this diverges by the divergence test. Do you see why we did a whole chapter on series before talking about power series? At x equals -3, we'll have the sum as k goes from 0 to infinity. Yes, we have -1 to the k. Here we'll have -2 to the k divided by 2 to the k. The 2 to the k will cancel. -1 to the k times -1 to the k is just the sum of terms all having 1. This, of course, diverges by the divergence test. It follows then that the interval of convergence is in fact equal to everything from -3 to 1, not including either endpoint. As you've seen, power series may converge at the right-hand endpoint of the interval of convergence, the left-hand endpoint, both, or neither. Let me give you an important theorem. Suppose we have a power series. We can start at 0, we can start at 1, but you can't start at -1 because that gives you division by 0 at x equals x0. Suppose that this power series has radius of convergence r. Let's call this f of x. It's just some function of x. First, f prime of x, which is the sum as k goes from 1 to infinity. At k equals 0, we have only a constant a0. Its derivative is 0, so when we take the derivative, we lose that first term. Taking the derivative just applies the power rule. We get k ak x minus x0 to the power k minus 1. The derivative has radius of convergence equal to the same radius of convergence as the original series. Taking the derivative gives you the same radius of convergence. The interval of convergence might be changed a little bit. You may or may not converge at an endpoint compared to the original series, but at least you know it will converge on an interval having the same radius. This part of the theorem implies that, first of all, any function that can be represented as a power series is differentiable. Not only that, but since the first derivative converges on the same open interval from x0 minus r to x0 plus r, then the derivative of the derivative will have the same radius of convergence as well. So not only is it 1 time differentiable for sure, you get 2 times differentiable with the same radius of convergence, and hence 3 times differentiable. This theorem will imply that every function that can be represented by a power series is not only 1 time differentiable, it's infinitely differentiable. On part 2, what happens if we look at the class of antiderivatives of a function that can be represented as a power series? You'll get a constant of integration, and the sum, as k goes from 0 to infinity, the only new term is the plus c. You'll have ak x minus x naught to the k plus 1 divided by k plus 1. You add 1 to the exponent and divide by the new exponent. This has radius of convergence equal to r as well. So when you integrate a power series, you get another power series that converges having the same radius of convergence. Again, it may differ about convergence at the endpoints, but everywhere on the open interval from x0 minus r to x0 plus r, you will get convergence. This theorem will motivate the definition of a whole new class of functions, so we'd better prove it. The radius of convergence on the derivative series is the limit. As k goes to infinity, the absolute value of k a sub k divided by k plus 1 a sub k. You can see that k over k plus 1 tends to 1. So the whole thing tends to the limit as k goes to infinity of a sub k divided by a sub k plus 1, which is the original radius of convergence. The proof for the derivative part goes in the same way, so we'll just call this done. A function is called analytic at x0 if it may be expressed as a power series centered at x0 having a positive radius of convergence. We want the interval of convergence to be non-trivial. Power series always converge at the center. So if the radius of convergence is 0, then that's kind of useless and meaningless. We want the series to be non-trivially represented as a power series on some interval in order to be classified as analytic. It follows from the last theorem that all analytic functions are infinitely differentiable. We'll express this statement as a corollary. If f is analytic at x0, then f is an element of the set of functions that are infinitely differentiable at x0. C infinity is the class of infinitely differentiable functions. We can modify this theorem to say that if f is analytic on some interval I, then it's infinitely differentiable at each point on that open interval I. we'll have the following notation. C omega of I is the class of analytic functions on the interval I. Note that C omega will be a proper subset of the set of infinitely differentiable functions. So far, we've been able to demonstrate that it will be a subset, but we need to show that it is a proper subset. And the way to do that is to exhibit a function that is infinitely differentiable, but not analytic at some point. We'll make that demonstration after we develop a little more theory. First, the basic theorem. If f can be expressed as a power series and this series converges on an interval I, if g of x also is expressible as a power series with the same center and also converges on the same interval I, then when we add these two series together, you can combine like terms, and to do that, you just combine the coefficients, because you can factor these out from the two coefficients. This also converges on the exact same interval I, and it converges to the sum of those two functions. I'm going to add on to that last theorem a little bit. If you multiply x minus x naught to the m you can write that as the sum as k goes from 0 to infinity, a sub k, x minus x naught to the power k plus m. Yes, you can add the exponents. And this will converge on the interval I as well. And it converges to x to the power x minus x naught to the power m times the original function f of x. Earlier in this lecture, we showed how 1 plus x squared and so on converged to 1 over 1 minus x, provided the absolute value of x is less than 1. It follows then, if we need x cubed over 1 minus x, a power series representation may be given by x cubed plus x to the fourth plus x to the fifth, and so on, the sum as k goes from 3 to infinity of x to the k. And this will also converge on the same interval. We've seen then that the sum as k goes from 0 to infinity of x to the k is 1 over 1 minus x on the interval absolute value of x is less than 1. What if we need a series for 1 over 1 minus x squared? We'll replace x by x squared here. When you take x squared and raise it to the power k, you multiply the exponents, and you end up with 2k. For what values of x will this converge? Well, everywhere that in absolute value, x squared will be less than 1. That's the same thing as the absolute value of x is less than 1. What about 1 over 1 plus x squared? The way to think of this is as 1 over 1 minus negative x squared. This gives us the sum. As k goes from 0 to infinity, we'll have negative 1 to the power k, and x squared to the power k, which is x to the 2k. Recall that arctan of x plus c is the integral of 1 over 1 plus x squared dx. That's the one. That's the one I asked you to remember. It follows then that I can integrate term by term to obtain the sum. As k goes from 0 to infinity, negative 1 to the k, x to the 2k plus 1 divided by 2k plus 1. I have a series that represents arctan up to a constant c. We'd kind of like to know what that constant c is, because I'm really looking for a power series representation of inverse tangent. To figure out what the constant c is, we'll use the fact that the arctangent of 0 is 0. And we'll evaluate at x equals 0 on both sides of the equation. We'll get c equals what we get when we plug in 0. Well, the right-hand side is clearly 0, so the constant of integration is in fact 0. That means we have a power series representation for inverse tangent of x. Arctan is this power series converging when x value is less than 1. In fact, it's easy to see that this will converge when x equals 1 as well. If we substitute x equals 1, we'll end up with an alternating series that behaves very much like the alternating harmonic series, which converges conditionally. So before moving on, what happens when we plug in x equals 1? The tangent of what angle is 1? The answer should be pi over 4. That will in fact be the sum, as k goes from 0 to infinity, of negative 1 to the k divided by 2k plus 1. Notice when k is equal to 0, you get 1. When k is equal to 1, you get minus 1/3. When k is equal to 2, you get 1/5. And so on. When you add these numbers up, you end up with pi over 4. This gives us a way of estimating pi. If you multiply both sides by 4, you get a representation for the number pi 4 times this series. It is a little intriguing that we can represent the number pi as a series involving only these rational numbers. However, the convergence of this series is rather slow. Since the series is alternating, we can use the remainder theorem for alternating series to determine how far out we need to go to get whatever decimal place accuracy we need. You'll find that you have to go pretty far indeed to get very accurate representations for pi from this series. There are other series that converge faster. Next, consider 1 over x. Now I'm going to express this in a very unusual way. I'm going to express it as 1 over 1 minus negative 1 times x minus 1. And I'm doing that because I'm going to substitute this into that formula for 1 over 1 minus x. We'll have the sum, as k goes from 0 to infinity, of negative 1 to the k, x minus 1 to the k. Now I'm not doing this just so I can represent 1 over x. I'm doing this because I can integrate and represent the natural log of the absolute value of x to within a constant of integration. It will be the integral of the series that we've constructed. That's going to be negative 1 to the k, x minus 1 to the k plus 1 divided by k plus 1. The only question is, what is the constant c? We can determine the constant of integration c by evaluating at x equals 1. The natural log of 1 is 0, and we'll be summing the sum as k goes from 0 to infinity of negative 1 to the k, 0 to the k plus 1 divided by k plus 1. When k starts at 0, we have 0 to the power of 1, which is 0. All of the terms end up being 0, which gives us the constant of integration equal to 0. We deduce then that a representation for the natural log is exactly this power series. Isn't it a little remarkable that some of the functions that you've come to know and love may be represented as power series? To go further down this path, we need to know what functions can be represented as power series. These power series are very interesting functions. They're all infinitely differentiable. Not only that, they're one level smoother than infinitely differentiable. They are analytic. We've said that there do exist functions that are infinitely differentiable at some point, but not analytic at that point. We'll show that in the next section, the section on Taylor series.